Hello, and thanks for joining me for this session, The Art of the State, Coordinating Services Using AWS Step Functions. My name is Gabe Hollenby, and I'm a Senior Developer Advocate here at Amazon Web Services. This is a bit of a long quotation, but it's a great one. Someone's talking about a reliable, automated way of orchestrating very complex queries and processes between distributed systems, saving time and money, gaining more productivity and agility, and making it easier to discuss solutions with non-technical stakeholders. Well, it's a quote from Paul Brown, a Senior Developer Manager at The Guardian. Here's the full quotation for you to read. As you can see, he's talking about a service called AWS Step Functions. In this session, I'm going to teach you everything you need to know to start working with AWS Step Functions to achieve these kinds of results in your own projects. We'll start with some background knowledge, discussing the lay of the land when it comes to working with distributed services, and we'll explore a common service coordination pattern called orchestration. We'll see how orchestration is a great fit for handling workflows with complex logic, and we'll learn how AWS Step Functions lets us build and execute these workflows in the cloud using something called state machines. Finally, we'll see some examples of customers using step functions and share some great resources to continue learning more. Let's start with an overview about how we typically get things done in the systems that we build. One way we build systems is with a monolithic architecture. It's often easier to start out this way with all of our application bundled together into one deployable unit. Here's a picture of a banking system full of various functionality, including document processing, identity verification, and more, all deployed as various code modules together with a common shared data store and analytics system underneath. But over time, what we usually experience is a need or desire to split up our monolith into a set of distributed services. Regardless of the size of each of these split-off services, we usually call this pattern microservices. Here, we split the work between multiple systems, which means we now have separate compute and data layers for each service. This is great because it gives us increased agility and scalability. We're free to have different teams work on each service with the languages and toolings that are best for each service. And we can scale each service for its independent needs. Some services will need more compute or database capacity. Others will benefit from multiple instances of the compute layer scaled horizontally. A microservices architecture makes this all possible. But a distributed system of services is almost always harder to coordinate, monitor, and debug. To tackle this issue, we typically turn to a service coordination pattern called orchestration. Let's continue to explore our example banking domain and look at how we might use orchestration to coordinate some services together. In this simplified banking system, we have 4 distinct services or areas of concern. An account application service, which is concerned with accepting applications for people who want to open a bank account and is responsible for returning an approve or reject decision. Next is a data checking service, which is responsible for performing various validations of data, such as checking the identity documentation of a bank account applicant or verifying that a home address appears valid. And next is the human review service, which tracks applications that need review and allows humans to make decisions about these flagged applications. And finally, we have the account service, responsible for creating and managing a bank account after a new account application has been approved. And here's how these services work in concert with one another. The account application service takes in new applications, performs the data checks required, flags an application for review by a human if required, and finally, passes approved decisions on to the account service. If you zoom out, here's what the same system looks like. And here it becomes even more obvious that what we have is an instance of service orchestration managed from the point of view of the account application service. After all, the account application service is the one making calls out to several other services and reacting to their responses in a stateful manner. When a new account application is received, it calls out to the data checking service to check the identity information provided in the application. It also verifies the address of the applicant. Then if any of those checks come back with a flag, a human reviewer will get involved to make a decision. Finally, if an approval decision was made, it calls out to the account service to open a new account. Let's look at these same steps required to process a new bank account application, but this time visualized a different way, as a sort of flowchart with more of the logic steps in it. First, we'll verify the identity documents provided by the applicant. Then, we'll check to make sure their home address appears valid. Then, we might need to involve a human to review the data in the application. Then we'll wait for the review to happen. And finally, we can approve the application. At first glance, this seems complete, but you might be jumping in your seat saying, "No, Gabe, this isn't enough. We can make it better." And I'd say, you're right. Let's see how. First, we don't need to be doing the identity check and the address check in a serial fashion. The result of one doesn't depend on the output of the other. So, instead, we could arrange to have these steps completed in parallel. Next, we can improve the steps that happen after the two checks are performed. We should explicitly encode a step to show that a human review is only required if the identity or address checks failed. So it's possible to go straight from the checks to an approved application. Finally, we should have an explicit step showing a rejected application and show that a human review step can transition to either an approve or a reject decision. There, that's much better. Now, you might not know it, but what you're looking at here is a state machine. A state machine simply describes a collection of computational steps that we want to split into discrete states. There's always only one starting state, and only one state is active at a time. You can think of this like a workflow or an executable flowchart. As the steps of the state machine activate, the active state is going to get some input, do something useful with that input, generate some output, and indicate the next state to transition to, passing the output from the current state into the input of the next state. This is such a powerful way to coordinate work that AWS has a specific service to work in this fashion. The service is called AWS Step Functions, and you can think of it as our service that provides fully managed state machines in the cloud. Step Functions lets you coordinate multiple AWS services into serverless workflows, so you can build and update apps quickly. Using Step Functions, you can design and run workflows that stitch together services such as AWS Lambda, AWS Fargate, and Amazon SageMaker into feature-rich applications. You can write resilient workflows with built-in error handling and retry support. And Step Functions can provide an auditable execution history with visual monitoring for your state machine executions, letting you visually trace and debug when needed. Let's see what this looks like in practice with a simple demo. So let's start with a submission that results in a successful application decision. I'm going to interact with my account application service by invoking a Lambda function from the command line. Here, I happen to be using the open source serverless framework to invoke the submit application Lambda function. You could ignore this detail, but if you're wondering what the SLS invoke command is, that's where it comes from. I'm going to submit an application with a valid name and address, and as we can see here, I've successfully submitted my application. The Lambda function that handles this application submission will pass the info it receives on to an AWS Step Function state machine designed to manage a similar application workflow to the one we reviewed just a few minutes ago. Now here in the Step Functions management console, I can see all of my state machine executions and drill down into this specific execution for my most recent submission. I can see my input and the final state machine output. In this case, the application was approved. I can scroll down and I can see the visual workflow showing exactly what happened during this specific execution. It starts with these two address checks. You can see both address checks returned false for their flagging output. I can also click into each of these validation states if I want to inspect each check input and output result on its own. And finally, I can click into the Approve Application state to see the final output, indicating that we transition to the Application Approved state. Now, I'll show a different flow through the state machine. Let's see what the execution flow looks like if we need to manually review a bad address that was submitted. So here I'm submitting a valid name, Gabe, but a bad address, one which doesn't match the address validation rules, which will cause the address check to return a true flag, causing the state machine to transition into a pending review state, waiting for a review decision to be made. The current state is highlighted in blue, which means the state is in progress. This means the state machine is still running and effectively paused, waiting for a callback from our review system to pass in a decision. We'll simulate that now back on the command line, issuing another call to submit an approved decision for the review. And if we're quick, back in the Step Functions management console, we can see in real time that the execution picks up again, ultimately resulting in an approved application and containing the state of the steps that came before it, including the review decision to approve the application. So now you've seen a step function in practice. Let me tell you a bit more about how AWS step functions work. First, some terminology. Each workflow you build is represented as a state machine, and each step in your workflow is called a state. When a step function executes, each move from one state to another is called a transition. And one cool thing about step functions is that by splitting up your workflow into discrete steps, you can reuse those steps among multiple state machines, and even easily view and edit the sequence of steps as your needs change. Each step function is defined by a JSON document that conforms to a specification described by the Amazon States language, a JSON-based structured language used to define your state machine as a collection of states that can do work, like task states, determine which states to transition to next, like choice states, stop execution with an error, like fail states, and so on. In the workflow shown here, we're using 4 types of states: task states to do work, a parallel state to do some work in parallel, 2 choice states to provide branching logic, and a special kind of task state integration that waits for a callback to proceed in order to implement our wait for review step. Let's dive in a little deeper and see how each of these contributes to our workflow. The task state performs work. This could be calling an AWS Lambda function, which is a very common use case, but you can also use task states to wait for a polling worker process running basically anywhere to pick up work from a step function, perform some computation, and return a result back to the workflow. And a task state can also be used to invoke APIs in other AWS services that step functions is integrated with. As an example, in our workflow, we use Lambda functions to do the work for all the steps in blue. Here's how we could define the first step that verifies ID documents. Each state is defined by a name and is represented as an object with various properties, which vary depending on the type of the state being defined. Here, you can see the state type is task, and it also has a resource property which contains an ARN of a Lambda function to execute, as well as a set of parameters to pass from the state machine state into the Lambda function invocation. The parallel state type, unsurprisingly, lets you execute work in parallel. It takes an array of state machine branches, which it will execute in parallel, returning an array of results from each state machine branch when they all finish executing. Here's how we could define the parallel state for our workflow. The type is set to parallel, and it has a branches property, which provides an array of objects representing sub-state machines to execute. Finally, it contains a result path property, which we can use to store the output from all the parallel executions, in this case, into a new state variable named checks. And it also contains instructions to transition to the human review required state next, when all the parallel branches are complete. The choice state type is like a switch statement from many programming languages. You give it an array of choice expressions, each comparing a state variable to some value, which the choice state will use to determine which state to transition to next, based on which choice expression evaluates to true, if any. Here's how we might implement the human review required step from our workflow. It's of type choice, and we pass 2 choice expressions in, each one looking at the check state variable that was returned from the parallel state at the top. If either validation check returned a flagged value of true, the state will transition to a wait for review state. Otherwise, it will default to transitioning to the approved application state. Finally, in some cases, we want to be able to pause state machine execution and wait for some external computation to happen. For example, we want to pause at the wait for review state until a human sees our flagged application and can make a decision. Once the human makes a decision, that review service needs to somehow tell this step function to resume execution, and it needs to pass in whatever value the state machine was waiting for. In this case, a decision about the account application. The way this works in step functions is with something called a task token, which step functions will generate for you automatically, ready to use in a task type defined with a special invocation style. When the external system calls back to step functions, it passes this task token back using either the sendTaskSuccess or sendTaskFailure API call, so that the step function system can find the appropriate pause task to pass the result to. Here's how we might implement this in our workflow. It's a task type, and this one involves a Lambda function as well. But the definition of this task type is a little bit different. Instead of just passing the ARN of the Lambda function we want to execute, we use a special resource type describing our intent to invoke a Lambda function and wait for a task token callback from an external system. Then we pass in the function name of the Lambda we want to invoke and the payload that we want to pass on to that Lambda. Here is where we pass the auto-generated task token value. In this example case, the flag application for review Lambda function might go and find an application record by its ID in some database, update its status to flagged, and persist this specific task token alongside it. Then, the application review system could show a human reviewer all applications with a status of flagged, and when approve or reject decision is made by the reviewer, the review system would call back to the AWS Step Functions API, passing in the review decision so the paused workflow could resume executing. When working with distributed systems, failures can happen for a number of reasons. Calls to some services might time out, tasks could fail for intermittent reasons, or you may even run into insufficient permissions issues. Fortunately, AWS Step Functions has a robust error handling capability. Each task state can be configured to retry when it encounters errors, with a configurable backoff rate up to a configurable maximum number of attempts. Tasks can also be configured to catch specific errors and transition to other states as appropriate. Let's see this in action with one more simple demo using a slightly updated version of our example workflow. Here, we've added a bit of logic to our Lambda function that checks applicant names to simulate an error, throwing a custom unprocessable data exception if it encounters a name string of unprocessable data. When we run this application data through our step function state machine, we know that our name or address check might fail due to receiving data that these steps cannot process at all. In this case, we want to catch errors and transition to a flag application as unprocessable state instead of submitting the application for human review. As you can see, we're able to inspect the execution and see that our step function caught the error. We can even view the exception to see more details. Now, you've already seen most of this in the demos from before, but just to explicitly call it out, here are a few points that nicely summarize the experience of how you work with step functions. You define your workflows in JSON. You can visualize these workflows in the management console, and you can even monitor current executions as well as audit previous executions there as well, allowing you to see the precise execution history and inputs and outputs of each state in your workflows. That covers all the basics of working with AWS Step Functions, but let's now dive a little bit deeper. Firstly, here's an exhaustive list of all of the state types defined in the Amazon States language today. You've already seen examples of most of these in this talk. The first one we haven't talked about yet is the map state type. This state type is very similar to the map function or concept from functional programming. In programming, you might use a map function to apply a function to each item in an array of values, returning a new array of the same size with the function results from each application. Similarly, the map state type allows you to process each of an input array's items with its own state machine, returning an array of results. What's even cooler is that you can configure the maximum degree of parallelism for the map state to use, which is incredibly useful for doing lots of work at once or limiting the simultaneous processing if you need to. Two of the other new state types we haven't talked about yet are the succeed and fail states. These are simple states that you can use to semantically signal a successful or failed execution. Each will cause the state machine to stop execution as well. Finally, the pass state type is very simple and allows you to just take input and pass it through to output without performing any work. It's very useful when you're first beginning to sketch out a step function workflow definition, as you can use the pass states like placeholders to be replaced by other state types later as you flesh things out. Earlier, I mentioned that step functions can integrate some of the APIs in a number of other AWS services. You've seen examples of invoking AWS Lambda functions in task states, but you can also perform work in these other services as well. Some particularly popular ones worth calling out include our Amazon ECS and Fargate support, allowing you to get work done via containers, the Amazon SageMaker integration, which is great for statefully managing your machine learning training and deployment workflows, and the ability for step functions to call back to itself, which lets you reuse logic between workflows by calling out to other step functions as needed. Well, I've been speaking a lot about the great things you can do with AWS step functions, but I'd be remiss if I didn't share with you how some of our customers are achieving great results using step functions in the real world. NIB Health Fund is one of Australia's fastest growing health insurers. They've got over 1 million customers across Australia and New Zealand. Now, the health insurance industry is highly regulated. Of course, you want to move quickly, but you need to do so in a safe and secure manner. For example, when someone needs to access into a secure computing environment, perhaps to break the glass and troubleshoot an issue, they need to use a jump box or bastion host to connect into these secure resources. At NIB, an operator can request permission to access a specific environment. At that point, an AWS step function begins a process that starts by notifying the required approver to make a decision to grant or deny access. It then waits for a response. Once it receives an approval response, it will kick off provisioning a securely configured bastion host for the operator to use as needed. Also, when the operator first requests access, they specify how long they'll need access to the secured system for. The step function state machine uses this information and starts a timer when the bastion host is created. When the timer's up, the bastion host is cleaned up automatically. Another great use case that I think is really nice and illustrates some of the non-technical values that step functions brings comes from Coca-Cola. The Coca-Cola company has many products that they manufacture, and these products need to have nutrition information on their labels. And of course, that means that whenever the product formulations change, or whenever labeling requirements from regulatory bodies change, they need to generate new labels. Believe it or not, it used to take them 36 hours to manage this whole process each time a label needed to change. And through the use of AWS step functions, they managed to get this down to only 10 seconds. That is such a dramatic improvement. I think it's worth talking about some of the key points that they highlight here, showing how step functions was so transformative in helping them achieve such dramatic results. The first point is that the data validation and transformation steps that need to happen in their pipeline can be designed visually with non-technical personnel. It's a huge advantage to be able to see your algorithm encoded as a state machine, a series of steps, and with the ability to generate these flow diagrams right there in the step functions management console. And the fact that these validation and transformation steps can be verified in real time as data is flowing through the state machine is really useful. As you saw in the demos a few minutes ago, as these step function state machines are executing, we can inspect their status in real time, seeing the current state and each step's inputs and outputs. This ability to inspect their data validation and transformation workflows in real time led them to identify and implement process optimizations right there on the spot. Speaking of getting work done dramatically faster, I would be remiss if I didn't also mention a new and exciting addition called AWS Step Functions Express Workflows. AWS Step Functions Express Workflows are designed to allow you to orchestrate compute, database, and messaging services at rates up to 100,000 events per second. They're suitable for high-volume event processing workloads like IoT data ingestion, microservice orchestration, and streaming data processing and transformation. Unlike the standard workflows I spoke about earlier, Express workflows are designed for short durations of less than 5 minutes, and they can be very cost-effective at scale for high-frequency data processing. Here's a quick overview of the standard workflows versus Express workflows. One salient point to call out here is that standard workflows can run for up to 1 year, while Express workflows can only run for up to 5 minutes in a single execution. Another point to call out is that you only get the execution history with tooling for visual debugging in the management console with standard workflows. Express workflows only send logs to Amazon CloudWatch. Also, Express workflows are not designed to support use cases that require the execution to pause and resume, like you saw with the standard workflow examples earlier in this talk. Hopefully I've inspired you to work with step functions the next time you need robust, fully managed service orchestration. But before I leave you, I want to share a few developer tools that I found useful when working with step functions and some tips for where to learn more. The first is AWS Step Functions Local. For testing and development purposes, you can install and run step functions on your local machine, which can be used to invoke AWS Lambda functions both in AWS and running locally. You can also use step functions local to coordinate other supported services. Next is Statelint, which is a command line tool you can install to inspect state machines written in the Amazon States language, helping you catch errors while you're writing your state machine definitions. If you're like me, and you're a fan of open source serverless framework tooling, you'll be pleased to know that there's a serverless framework plugin for working with step functions. And finally, because I like working in Visual Studio Code, I really enjoy the AWS Step Functions Constructor extension for VS Code, which gives you a nice visual preview of your state machine as you're writing it in a similar manner to the experience you get when working in the management console, but this is right in your editor. To continue learning more about AWS Step Functions, here are the 3 links I recommend the most. The first is a self-guided workshop you can do at your own pace. The second recommendation I have is to spend the time to read through the Step Functions Developer Guide documentation. It's not very long, and it contains a ton of useful info and examples to help you learn quickly. And finally, you can visit the Step Functions website to see a number of popular example reference architectures to solve many common problems using step functions. To sum up, I just want you to remember that AWS Step Functions gives you a fully managed service with high availability and automatic scaling built right in. If you use step functions to orchestrate your workflows, you'll get visual monitoring, auditable execution history, and robust built-in error handling. And of course, with AWS Step Functions, you only pay for what you use. With standard workflows, you're charged based on the number of state transitions required to execute your application. And with Express workflows, you're charged based on the number of requests for your workflow and for the time and memory it takes for your workflow to execute. This means, for example, that standard workflows don't charge you for the time they spend in waiting states, and Express workflows are likely going to be more cost-effective at processing large volumes of executions that finish quickly. Well, I hope I've inspired you all to give AWS Step Functions a try. So what are you waiting for? Step up and go build. Thank you so much for taking the time to stay with me for this session. Your time's valuable, and I appreciate the chance you've given me to share this with you today. If this talk helps you to build something, I would love to hear about it. Please keep in touch on LinkedIn and Twitter. Thanks again.